Hello.
Hello, everyone.
Let me get
Okay. Yes, I should have made you co-host, so you should be able to share your screen.
That's great. I will try in a second.
Okay.
Just making sure that the screen I want to share will be properly organized, that I'm not polluting it with unnecessary stuff. All right. Let me have a look.
Yeah.
Let's try this now. So you should see my first slide of the deck, I guess.
Yeah.
So then
Yeah,
everything
we can
is
see.
ready to go on my side.
Perfect. I would say let's wait a few more minutes.
Sure.
Because people are coming in, and then
I
we
will
can
also
start.
allow you to do all the introductions, and I will mute and wait for your sign.
Yeah, I think that works. Okay, I think that we can start, and people will keep coming in, but I think, yeah, to not lose more time, we should start. Welcome, everyone. Again, I'm also here just to support in case something is needed, but other than that, I'm just here also to record the session. So, yeah, let's start.
All right. Thank you, Marta. And thank you, everybody, for being here and being interested on this brief training on mathematical optimization. So I think we will indeed start, and I see that there are 32 participants already on board. Feel free to join. And we will start slowly. So I think that the couple of minutes that will follow from now are still okay if people are entering this meeting. So the meeting is indeed about mathematical optimization, or this presentation, this training is about mathematical optimization. I will start by introducing myself. So I'm Joaquim Gromincho. I was born in Portugal some time ago, and I came to the Netherlands also some time ago, and I'm still based in the Netherlands. I joined the company called Ortec, which you may already have heard about because it's one of the companies supporting the ABW. I had many roles there. I've been with that company for 27 years now, and I am now Science and Education Officer. I've been with the University of Amsterdam for about 3 years now. I moved to the UVA from another university in Amsterdam where I spent some time before, and I've been combining these, let's say, these two parts of my professional life, one in industry with one at the university, for about 23 years now. At the University of Amsterdam, I'm professor of business analytics as part of the Amsterdam Business School. And I have been quite involved with the Analytics for a Better World Institute for, I think, since the installation of the institute. And my role there is that of a lead optimization architect. I like to see myself as somebody that bridges theory with practice. And in the Netherlands, we have a Society for Statistics and Operations Research. You can see that as important pillars of analytics. I'm the editor-in-chief of a glossy magazine that we publish within that society. And I'm also somebody that indeed, in a global way, tries to bridge, let's say, from theory to practice in applying analytics, and in particular operations research, which is part of analytics. And I'm part of the steering committee of Practitioners Forum within the Euro. Euro is, let's say, the collection of all the operations research societies in Europe. So that's me. I would love to meeting all of you, but in view of the time, I think I will just proceed with my intended lecture today, and maybe we will have opportunities to have discussions later on during this training. So you must have seen this graph many times. I think this graph is probably being part of the training that you are having from the ABW at some moments, and it tells you that analytics is something that starts in a descriptive way by just telling you what the data says about what already happened, and it goes all the way up to becoming able to make things happen. And when you think about making things happen, that's all about taking decisions. And prescriptive analytics is that part of analytics that involves taking decisions. And in particular, one of the instruments that you can use to take decisions is applying optimization, and optimization, in particular mathematical optimization, which is exactly what we are going to be talking about. So we are going to be zooming in somehow that part of the analytics spectrum, let's say, which is on the top right, so more or less on the top of what you can do with analytics. But we will just be giving a bird's eye view to what is that all about. And in fact, what I intend, I hope that will be our objectives that we meet today, is that my presentation, I hope it will be appealing to both of you that are either very curious about analytics in a more or less methodological way. How can we do those things? How can we apply, for instance, Python? And those that are already more or less familiar with those methodologies and want to learn a bit more about mathematical optimization. I will try to divide my training in stories, and I think that stories are valuable when it comes to remembering what you heard. So I hope that you can hang this knowledge somehow to those on those stories. One impression that I want to give you is that Python, which I believe it has been a language adopted by most of the trainings that you have been following, and something that you can use in your own practice, is indeed a very powerful language, because just a little bit of Python will enable you to see a lot of results. I hope that you will also witness that during this training. But most importantly, I want to indeed tell you what the value is of prescriptive analytics and what the role is of mathematical optimization in achieving that value. And one important thing about mathematical optimization, which is quite unique, is that if you have a model and if a solver tells you that the model has been solved to optimality, then you know that no better solution exists. You can search as much as you want, but you may find solutions of equal value, but no solution can beat the one that the solver has proclaimed to be optimal. And I also want you to get the feeling of what mathematical models are all about and what it means to express a model from data and express a model, feed it with the data that you have, and call a solver to find that optimal solution. In the end, I will illustrate with two projects that relate to the, let's say, Analytics for a Better World Institute. And I want to reassure you that these may be quite ambitious, but I want you to sit down and relax. Everything I will tell you is complemented with notebooks that you can use at your own time, and you may find it maybe sometimes as going too fast, but you can go back to the materials in your own time, and feel free to reach out to me if you have any questions afterwards. So I think that this is what I want. I hope that we will be able to get close to these objectives during this training. And just allow me to have a very brief question to you. And oh, somebody gave me a compliment in the chat. Oh, thank you, Ayman. Apparently somebody listened or watched a video of a recording of a training I gave previously on statistics. And if you are here today after watching that video, then I made a good impression. Thank you so much. Otherwise, you probably would have felt that you would spend better your time. Thank you so much. I will ask you just to give me an answer to a very brief question by raising your virtual hand in the meeting. So I will ask you to raise your hand if you use Python sometimes already. Okay, I see many hands being raised. Let me just see if okay, I see 15 already being raised. All right, so 17, we are approaching half. And now I don't see any changes anymore. So there are many of you that use Python, and then maybe just as many that do not. So Python will be part of this training, and it will be part of what you can do by yourself later on, because I will be using notebooks, as I mentioned. But it's hopefully not an impediment to understand what the intended message is, even if you don't use Python. So I hope that you can still understand where I want to bring you in this nice journey that we go, that we'll be doing today together. All right, so let's proceed. I have mentioned that it is all about mathematical optimization today. So I think that I should start by telling you what mathematical optimization is. And that's exactly what I will try to do in the first minutes of this training, or in the next minutes of this training. And in order to tell you what mathematical optimization is, I will tell you the story of Alice. So Alice is a girl that once received a beautiful rose, and she was very happy to have that jest of affection. I mean, a friend of Alice came to her and gave her this beautiful rose. And Alice was so happy about the rose that she decided to take very good care of that rose. And she looked for a vase. She could not find a vase, but she found a lemonade glass. And with that lemonade glass, she thought, okay, I can put my rose inside, and it will be a good place for my rose to stand. Unfortunately, when she placed this long-stemmed rose inside the glass, she discovered that it was not very stable. I mean, the rose had a very long stem, and the glass was not as tall as the rose, and everything fell. Then Alice thought, well, I know that roses enjoy some water. If I give water to the rose, it will be good for the rose. It will also be probably good for the whole stability of this construction. Maybe a little bit of water will help the rose to stand still in the glass. And it did. She added a bit of water and everything stood. And then she thought, okay, a bit of water helped. Let's be very safe and fill up the glass with water. And then she realized in distress that everything became just as unstable as in the beginning. And it also felt, and the only difference is that the whole thing became much more wet. All right. Can you imagine the distress of a rose? And I see Kashif raising his hand, or maybe it's still from the previous question. Kashif, do you want to ask something? No, maybe not.
No, it was an old.
So if you want to ask something, you can just unmute. I will be hearing you, and it's not a very big group. Just interrupt me, or if I do not hear you for any reason, reach out to Marta and she will help us out. Okay. I believe you can understand what Alice felt. I mean, she felt curious. She thought a bit of water helped. A lot of water did not help. So what could be the ideal amount of water to put in this glass in order to make it as stable as possible? And she even worded in such a way, what is the optimal level of water in terms of stability? Well, of course, that in order to answer this question, you need to at least translate the question to something that you can deal with. And that's exactly what Alice did. So she realized that it is all about the glass with water and the way that this glass with water actually balances. There is a point in the glass with water, the so-called center of gravity. Well, the whole thing is balancing. And she understood, well, if that point is very high, then the rose will tip it off. If that point is lower, then it will become stable. So basically, the aim of finding the optimal amount of water translates into the aim of lowering that center of gravity of the glass with water. And you may feel like, oh, this is becoming too much physics. Well, it's not. So let's proceed a little bit. In order to understand what the center of gravity of the glass with water will be, we first need to think about the center of gravity of the empty glass and the center of gravity of the water inside the glass. And a little bit of common sense will tell you if the glass is just like a cylinder on my picture, then the center of gravity of the glass, when it is empty, it's halfway the height of the glass. And the center of gravity of the water inside the glass, which is going to take the same shape as the glass itself, it's going to be a cylinder of water, it's halfway the height of water. So what we want now is to figure out where is the center of gravity of the glass with water. Well, fortunately, Alice knows very well how to balance masses. She's a child that likes to play, and when she sits on a seesaw with a friend, she knows that if the friend has lower mass than she does, then she should move a little bit closer to the fulcrum, and if the friend on the other hand has higher mass than she has, she moves a little bit further away from the fulcrum and maybe the friend a little bit closer. So that's the way that you balance masses. And balancing masses has been formalized long ago by Archimedes, who found out that these things are actually very proportional. So the point where everything balances is the point where the mass on the left and the distance to the fulcrum multiplied will equal the mass on the right and the distance to the fulcrum multiplied. So this is something that she learned from Archimedes, and then by just grabbing a piece of paper and a pencil, she realized that the height of the center of gravity of the glass with water would be some way in between the height of the center of gravity of the water and the height of the center of gravity of the glass, but that point in between would be such that the proportion of the mass of water when taken on the total mass of the glass and the water would be the distance from the center of gravity of water taken from that point to the center of gravity of the glass. So if I would move up a little bit, it will be in between these two, but how far in between depends on the proportion of how much of the total mass is water and how much of the total mass is glass. So actually, this formula right here. And then what she can do with her piece of paper and her pencil is to feed in some data. She can observe that her glass is 20 centimeters tall, is 4 centimeters wide, and it has like 100 grams of mass. And she grabs her pocket calculator and she starts plotting some values that she can compute from that formula. When she has no water at all, then the center of gravity will be halfway the height of the glass. Then she starts adding water, and she sees that the center of gravity of the glass with water is going down, and then it starts going up to reach exactly the same value halfway the glass when the glass is full. And it all makes sense to her. That's why it became so unstable as it was in the beginning. But what she's looking for is somewhere here, somewhere between, let's say, 6 and 8, where it seems like it is attaining the lowest possible height. So the center of gravity of the glass with water will be as lowest as it can be. So these are just some points that she computed. She computed it for height 2, height 4, and so forth, just 10 points. But she understands that these 10 points are actually part of a bigger story, right? So there is a function, a mathematical function that goes through these points and even in all the points between. And she's looking for a minimum for that function. And then she wonders a little bit how to do that. She finds out that this gentleman, just like Archimedes found out to balance masses, this gentleman figured out how to find such minima. And it happens to relate to the derivative of that function. It's a bit of mathematics, but just for you to understand that mathematical optimization, the word mathematics stands for something. There is some mathematics there. And so Pierre de Fermat actually discovered that the point that she's looking for is a point where the derivative goes to zero, becomes zero. And then she could actually do that. She already knew about derivatives. She computed the derivative, made it equal to zero. And she realized it's more or less about 1/3 of the height of the glass. And she had learned even more. She knew that by computing the second derivative on the same point, she would be able to tell whether it was indeed a minimum or a maximum. This is a little bit of mathematics, but just to give you the following piece of information. Mathematicians know how to deal with these problems. Mathematicians know how to find and identify optima. That's important. So it's important. Why? Because we can summarize the story of Alice and her flower by telling you that you have just learned what a mathematical optimization is all about. The anatomy of a mathematical optimization model is the following. There will be decision variables. For Alice, the only decision that she can take is how much water to put in the glass. And she expressed that decision in terms of the height of the water. So her decision variable is the height of the water that she can put in the glass. There is an objective function. For Alice, that was the center of gravity of the glass with water. And for that objective function, she wanted to bring it as down as possible, which is the aim for the objective that we see down here. And there are some functional constraints. Both the objective function and the constraints should be expressed on the same decision variables. So the center of gravity of the glass with water is a function of the height of water. And there is, of course, the constraint that you cannot put less water in the glass than nothing and not more water than the height of the glass. So this is something that will come back on any mathematical optimization model. There will be decision variables, there will be an objective function, there will be functional constraints, and you have an aim for your objective. You want to have it as low as possible or as high as possible. So you already learned what a mathematical optimization problem or model is all about. You also learned that mathematicians have found ways not only to model the problem at hand, that's what actually Alice did. For that, you always need some domain knowledge. And for Alice, the domain knowledge that she needed was provided by Archimedes. I mean, by knowing how to balance those masses, she could model what is the center of gravity of a glass with water. That is the function that became the objective function. And mathematicians can also determine, describe, and characterize optimal solutions for such models. That's what Fermat did. And so far, for the story of Alice, the constraints did not play a very important role. The constraints did not play a very important role because the optimum happened to be somewhere inside the feasible region, and the feasible region is all the possible choices that you can take. So the optimum actually happened to be somewhere in there. Therefore, the constraints were not too important, but they will become important a bit later. And you also learned already with the story of Alice that you may solve such problems with pen and paper, but most of the problems that are relevant for us cannot be solved with pen and paper anymore. So they will be solved with a computer. And the computer will declare the problem to being solved optimally. And now you know that there should be some kind of mathematical guarantee that the problem has indeed been solved optimally. And that guarantee leads to the last thing that you have learned with this story. Nothing beats an optimum. So once Alice knows that 1/3 is the ideal height of water, she will be always filling her glasses or her vases with 1/3 of water from now on. Okay, was this story understandable? Please raise your hand if you are completely lost. Oh, apparently everybody is with me. That's good news. That's good news. So let's proceed. So there will be Python in my notebooks, and my Python will be using a package called Pyomo, which is a package for modeling optimization problems. If you want to learn everything about this package, you can consider finding this book. It's also available online. You don't have to buy it, but it's a very technical book. I don't advise you to try to learn mathematical optimization from this book. This book teaches you exactly how to do things in the package Pyomo if you already have a feeling about what you want to do. And in order to give you an impression of how Python can help you do these type of things, I will complement each of my stories with a notebook, and there will be, of course, a notebook for the story of Alice. And if you click on such links, you will be brought to a notebook hosted by Colab, and you can see that this notebook is part of another training, a training that I give with my colleague Niels van der Laan. But this notebook is indeed about the story of Alice. You may see that there are even here other links that can bring you to stories that I'm not telling you today. So if you really feel excited about this and you want to know more, then you also can learn about Betty. We will learn about Caroline later. Today we will skip Betty. And we'll also skip Dina. We will go a little bit further and bring our training closer to let's say, to examples that relate to the Sustainable Development Goals in the end. But if you open this notebook, you will see that the story of Alice is told again here, and there are all the mathematics that I've told you in my slides. And then there is a bit of Python to do different things, including solving the problem analytically. And here you see it being solved with numbers. You can also solve it with Python symbolically, which means that Python can also give you the same formulas that you would do with mathematics and a pen and a paper. And you see all this happening. You can also see Python drawing the curve of the center of gravity of the glass with water and marking the lowest point there. And then you enter the point where you can actually formulate the model using Pyomo and ask a solver to solve it. And this is for the simple problem of Alice, what the Pyomo would be to model this problem. You get a model. That model gets a variable, which is h, the height of the water that you had. It's bounded between 0 and 20 because that's the height of your glass. You want to minimize your objective, and your objective is this formula, which is the center of gravity of the glass with water. And Esme raised her hand. Esme, please tell me.
Yeah, hello. I just wanted to ask if you could share the link to the notebook maybe in the chat so that we can easily copy it.
Oh, maybe I lagged one thing, which was to give you a PDF or something to click around. In the first break, I will make sure that you get a PDF, but right now I will, of course, do as you suggest. It's a
Thank
very
you so much.
suggestion. I will just put the link to the notebook on the chat, and if you click on it, you will be able to see the same thing on your browser. Thank you, Esme. Thank you very much. At some point, you will be able to see on your browser what you are seeing on my screen. And for the optimization problem of Alice, this is all the Python you need. You declare the model, you declare a variable in the model, you give it an objective, and because your variable has these bounds, also the constraints are more or less tackled. I mean, the variable itself carries its constraints in terms of those bounds, and this is the model. It's a very small piece of Python. You can also ask it to express itself in text, but more importantly, you can solve it. And for this mathematical optimization models, there is even a place on internet, which is called NEOS, which hosts a lot of solvers. And you can actually send your model to this place and say, I want that solver to solve it. And there are many solvers to choose from. And you may ask, how do I know which solver is adequate? I will give you some reading suggestions for that if you really want, because you may end up on the following page, you may end up learning a bit about mathematical optimization and not doing it yourself, but making sure that your team needs to have somebody that can do this, okay? But if you want to do it, and if you just want to play with a bit of Pyomo and deploying it into some solver, you don't even need to install your solver. You can send it here. And that's exactly what is happening here. I'm sending that model to NEOS and asking it to be solved by IPOpt, which happens to be a very general solver. And then there will be the solution, and the solution is this one. And it took some time. It took like 9 seconds to do a round trip through the internet to that solver, wait for its place in the queue, because that solver, that server with a lot of solvers is there for everybody to use. You may end up waiting a little bit, but 9 seconds later, you got your solution. But this can become even more exciting when you learn that most of the things you want to do with mathematical optimization also has free solvers, which are completely open source, completely free, that you can install on your own machine. It's also the case for IPOpt itself. A little bit higher on the notebook, you see that I'm actually installing IPOpt in my Colab. And then a bit later, I'm going to solve the problem locally. Of course, I say locally between quotes, because this is deployed on some Google Cloud. This Colab thing is running somewhere, but it will be solved on that specific session. And it's taking just 100 microseconds, because there is this round trip on the internet. It's not there anymore. It's just being solved there, and you get the same optimal value. So there are also some conclusions that you can take from this. So this complements the story of Alice about deciding how much water to put on a glass of water, with some Python that can help you understand how to do it with symbolic mathematics, and also with a mathematical optimization model that you can solve with the solver. Are the learning objectives of this part at least clear? I will always ask you, if it is not the case, raise your hand. All right. I see no hands being risen, so it sounds like it has been clear. So we learned about what is a mathematical optimization model. There are decision variables, there are constraints, there are objective functions. And once you get all that fed with your data, with numbers inside those formulas, you can ask a solver to find your solution. And that's what we did with Alice. And for Alice, we found that solution that we could already have found with pen and paper and a bit of Fermat by finding the derivative and everything. But what are the optimal solutions of more complex problems? More complex problems, what makes more complex problems is the presence of constraints that actually constrain your feasible domain in some sense. And I like to tell you a bit of history as well. I always find that these people that have contributed to these fields are kind of heroes. So we already met Archimedes, and then we met Fermat. We are meeting Lagrange now. Lagrange was the first mathematician to understand how to deal with constraints. In the beginning, he only we could only deal with constraints of the type equality. So like a function equal to anything. Well, it can be equal to 0 without, like we say in mathematics, without loss of generality, means that if it is not 0, then you put whatever it is to the left, and then it becomes 0. So when I write things like equal to 0, does not mean that the constraint always equals to 0. It only means that whatever it is not 0, it's on the left of this equality. So this is just a bit of mathematics. Do not worry too much about it, but Lagrange learned and understood and told us how to deal with equalities. But for instance, for Alice, the equality is not the case. I mean, she should have two inequalities, bigger or equal than 0 and less or equal than 20. It took a little bit longer before this gentleman, William Carouche, understood how to deal with inequalities alongside with equalities. And he did that on his master's thesis. So actually, him and his supervisors were aware of his findings, but the rest of the world stayed unaware of his findings until two professors, Professor Kuhn and Professor Tucker, discovered the same thing. They formulated the theorem. They even got the prize for it. And then later on, people understood that it was found before by Carouche. So now we talk about the Carouche-Kuhn-Tucker theorem of the Carouche-Kuhn-Tucker conditions of optimality. And this is very important because when a solver tells you that the problem has been solved to optimality, this is part of the guarantees that the solver could establish. And if you want to understand what it means is on your slide now. It means that there are two forces that balance in such a way that you get stuck on that point. So there is one force that wants to improve the objective function, another force that wants to maintain feasibility. And if you cannot take any step that improves your objective function without compromising feasibility, then you are at least at the local optimum, and some additional mathematical properties can express that optimality in global way and tell you that the optimum is global. In order to tell you what it means, I will just make some drawings. And there is, of course, a lot of mathematics that I'm not covering, but let's try to understand the picture on the right. The picture on the right expresses a kind of a mathematical optimization problem with two decision variables, variable x1 and variable x2. I'm drawing them on those two axes, the horizontal and the vertical x. So when I'm looking at that drawing, I'm not looking at the drawing with the objective function value in it. I'm looking at the drawing of the feasible region. The objective function is somewhere outside that space. And also the constraints are drawn there as lines that mark the boundary of what they delimit. So I have like the constraint G1 says that something to one of the sides of these lines is feasible, and this says that something to one of the sides of these lines is also feasible, and being outside that line is infeasible. These are what we call isolines, and you see them on the weather reports all the time, like the lines of the same pressure and the lines of the same temperature. Those are isolines. So these are isolines for constraints, and this point here is a point where I'm at the boundary of those two constraints, the constraint G1 and G2. I'm actually where they meet, and if I go one step to one side, I'm infeasible. If I want to stay feasible, I should go to the other side. And then you need to know what is the good side, of course. And in order to know that, in mathematical terms, you need to know something about derivatives, and in more dimensions, that's gradients. So there is, for the objective function, the gradient of the objective function says it goes up that way, it goes down that way. That's the gradient itself, the negative of the gradient. So if you are minimizing, you want to go along the dashed line, and if you are maximizing, you want to go along the solid line. So if you are maximizing, you want to go that way. If you are minimizing, you want to go that way. And then there is, of course, a story that the constraint tells. This is what the objective function wants. You are minimizing, so you want to go to this side of this line, what we call this half space here. And then the constraint tells you if you want to stay feasible for G1, you should be on that yellow part. And if you want to stay feasible for G2, on that light blue part. And then the intersection of everything that keeps you feasible is what we call the feasible cone, is that part over there. And the objective function wants to go out of that feasible cone, and then you are stuck.
So in mathematical terms, it's exactly the same as I told you with the two donkeys. You cannot take any step improving the objective function without compromising feasibility. Then you are at the local optimum. In order to make it a little bit more clear, and please raise your hand if this was very abstract for you. I expect many hands. Don't be shy. This was very abstract for you, right? The only thing, there are two people that say this was very abstract for me, and there are some others that are maybe shy. The only thing that I want you to remember is, okay, there are more people telling it was very abstract. All right. It was not intended, but it was intended to tell you the following. If a solver tells you, after solving a problem, that the optimal solution has been found, there is mathematics behind it. So there is mathematics that enable the solver to tell that the problem has been solved to optimality. And the mathematics look like this. That's the purpose of this message. I want to give you a glimpse under the hood of mathematical optimization for you to understand that if a solver tells you the problem has been solved to optimality, there is some kind of guarantee of optimality. And that will come back in the next story. The next story is the story of Caroline. And after we deal with this story, we will have a very short break. And there will be a second part of the training and a third part of the training. There will be two very short breaks. So I see that Sola still has a hand risen, maybe because of the previous question. Or if you just want to say something, please unmute. You can always interrupt me. So I have now the next story. And the next story is going to be a little bit more, let's say, a story that may relate to real life in terms of there is some business here, and this business wants to achieve like an higher profit, things like that. And then later on, our stories will become more related to sustainable development goals. But for now, let's meet Caroline. Caroline is a very entrepreneurial girl who has a factory that produces two types of trophies. Her business is to produce trophies, a trophy for football matches and a trophy for golf matches. I mean, there is a football trophy that you can award to the winning team and a golf trophy that you can award to the winning player. So the golf trophy probably looks like this picture. There is a wood base, a plaque, and an ornament, and the ornament is a golf ball. And then there is something similar for football. The difference being that you use more wood for the football trophy. You use 4 decimeters of wood per trophy, while you only use 2 decimeters of wood per golf trophy. So wood is used in both. There is a plaque also in both, like this plaque here. There is a brass football on the football trophy, and there is a golf ball on the golf trophy. And then you also have your expected profits, like you expect each football trophy that you produce to give you €12 profit, and each golf trophy that you produce to give you €9 profit. And then Caroline is also aware of her inventory of raw materials. In order to produce trophies, she needs footballs, she needs golf balls, 1,750 plaques, and 480 meters of wood. That's what she has in her inventory. She has like 1,000 of those, 1,500 of those, and so forth. Knowing the inventory, she only has 2 decisions, namely how many football trophies to produce, how many golf trophies to produce, and everything is a follow-up of taking such decisions. So each football trophy that she produces will consume wood, will consume 1 plaque, 1 brass football. It will yield €12 profit, and so forth. So after you read this, if you think for a while, and if you place yourself in the role of a mathematical optimization analyst, then you will be able to solve these. And you will be able to solve these with the aim of finding the optimal production plan for Caroline, which actually dictates how many football and how many golf trophies she should produce, while respecting the raw materials, availabilities, and maximizing their profit. And Caroline knows how to do this because Mr. Kantorovich actually told us how to do this. Mr. Kantorovich ended up getting a Nobel Prize for his findings. Well, it came a little bit later, because when he invented all these. He was at the other side of the Iron Curtain, and it took a while before that Iron Curtain was opened, and the Nobel Prize Committee found about all these things. And what he actually discovered, and he gave him a Nobel Prize in economy, in economics, was that you can translate this type of questions into mathematical models by naming your variables. So let's say that the number of football trophies to produce is x1, the number of golf trophies to produce is x2, and then expressing indeed your situation in very simple mathematical terms. And in this case, all the formulas used are just linear formulas. So I only have numbers multiplying by variables and adding with numbers multiplying by variables. So this is what we now call linear optimization models. And this is exactly what Mr. Kantorovich discovered many years ago. So we have an objective function that tells us that our aim is to maximize the total profit, which is 12 euros per football trophy, plus 9 euros per golf trophy, that each football trophy consumes one football, and there are 1,000 of those. Each golf trophy consumes one golf ball, and there are 1,500 of those. Each trophy, regardless of being football or golf, consumes a plaque, and there are x1 plus x2 of those trophies, and I have 1,750 plaques available. So each trophy produced consumes one plaque, and I can only use as much as those. And then I have like 4 decimeters of wood per football trophy, 2 decimeters of wood per golf trophy, and I have 4,800 decimeters of wood available. And this is the equation that tells me how much wood is limiting my production. So my production is limited by the number of footballs, the number of golf balls, the number of plaques, and the amount of wood, and I should never produce negative things. So do you understand how the story of Caroline translates into this bit of mathematics? So there is a mathematical model for the story of Caroline. And that also means that I can end up putting this mathematical model in some Python, solve it, and get the optimal solution out of it. But the story of Caroline is very simple. I only have like 2 variables, so I can actually understand a little bit better how these solutions are found by just doing a drawing along the same line of thought as I did that hypothetical drawing for optimality conditions. So if I have like x1 and x2 as being the number of trophies of the type golf, and that's x2, and the type football, that's x1, I can draw that, and I can draw it by just drawing like the first quadrant of this axis. Because why? Because I know that all my variables of interest are big or equal than 0. So I can already draw it in this way. And then I start putting everything of my model in it. So x1 is big or equal than 0, means that I'm to the right of that line. x2 is big or equal than 0, means that I'm above that line. I also have x1 smaller or equal than 1,000, x2 smaller or equal than 1,500, x1 plus x2 less or equal than 1,750, and then the 4x1 plus the 2x2 less or equal than 4,800, meaning that the points of interest, the feasible production plans for Caroline, are inside this region delimited by those straight lines. So this region here is what I call the feasible region of my decision process. I have to decide how many football trophies and how many golf trophies to produce, and whatever I come up with should be inside this region, otherwise it's not feasible. The question is now which one is the best? And in order to understand which one is the best, I will now forget about those points. They were used to just draw these things, and I will look at the objective function. The objective function is the 12x1 plus the 9x2, and that function will be on different places depending on the solution that I want to consider. So if the solution that I want to consider is just to have like no production at all, which is feasible, like 0, 0 is feasible, no problem, then it yields nothing, but it will yield nothing on any other point on this line. So this is the ISO line for the objective function. And if I move that function that way, it's increasing the value. So now every point on this line has a higher value than 0. And it goes on increasing until it meets that point over there, where it cannot take any step further without compromising feasibility, which happens to be a Karushkan-Tucker point, or a point where those forces are balanced. I cannot improve any further without destroying feasibility. So that's my optimum. So, and that optimum is the point where the line x1 plus x2 equals 1750 meets the line 4x1 plus 2x2 equals 4800. And if we just solve this system of two equations to two variables, I get this solution. So I could do this with pen and paper because I could draw it because it has only two variables. And I can tell Caroline, okay, Caroline, you should produce 650 football trophies and 1100 golf trophies, yielding you a maximal attainable profit of 17,700 euros. And you will end up producing indeed these many trophies, but using all but 350 brass footballs, using all but 400 golf balls, using all the plaques and using all the wood. So this is a story of Caroline together with an optimal solution. Oh, there is an hand raised by Martina. Tell me.
Yes. Yeah, maybe could you go back to how you determined the formula for that line that you were sliding over it? Like
the line that I was sliding around.
Yeah, okay. That green line. Yeah, how did you come up with that?
Yes, the green line actually represents the objective function, the 12x1 plus a 9x2. But there is nothing to equate this line against. I mean, for the constraints, I have like these boundaries. That's how I can draw the constraints. But the objective function will take different values depending on the x's. So it will take different values. So I'm putting that line on different positions. I started by considering the situation where the x1 is equal to 0 and the x2 is also equal to 0, which happens to be feasible. So that's actually that corner point down there. And now I'm putting 12x1 plus 9x2 equal to 0. And that's this line. So along this line are all the points on the plane x1 and x2 that yield the total value of 0 to 12x1 plus 9x2. And because that's feasible, I know, okay, I could do that. But because of my intent of bringing the value of this line as high as possible, I discover that I could take points on this green region, and I can take points more to this side, and it will up stopping there while aiming at getting different values, which are increasingly higher than the previous one. So each parallel position to this line will either be higher than the previous one or lower, depending on whether it's going that way or that way. And actually, that's following the vector 12, 9, which happens to be the gradient of this line. So if you follow that vector, you go up. If you follow.
And how did you come up with that vector or with that 12 and 9?
I imagine like I have like a ruler on this drawing, and I'm just shifting it parallel to itself while maintaining the inclination of the line, but just shifting it into points that giving it increasingly higher value.
Okay, yeah, but like I think still my first question I still have, like, how do you know the steepness? Because it could also be like less steep, right? So how do you come up with 12 times x1, the 12 and the 9? Like how where did you
I read it from here. How did
you come up with it?
How did I come up to writing it here? Then I read it from here. So Caroline knows
the prices. Yeah.
Each trophy of the type football will give her 12 euro profit.
Yeah.
Each trophy of the type golf will give her 9 euro profit. So there is a first step, which is translating the story into a mathematical model. So this is the way that mathematics capture the story of Caroline in a mathematical model. And then the second step is to solve it for the data at hand. So the data is also already written here. So I have all the numbers filled in. So I only need to solve it. And I did that graphically.
Yeah, clear. Thanks.
Okay. And that's the solution. And then you may wonder, how are the solvers doing this? Because apparently I could draw it for two variables, but it's not very likely that the solvers are actually drawing some things inside the computer. No, they are not. So it took us until this gentleman, because this gentleman actually invented the first algorithm that is able to solve any linear optimization problem whatsoever. And that did not give him any Nobel Prize, but it gave us a very useful technology to use. And basically what happens is, I can illustrate it on the same drawing. What happens is the following: mathematicians could prove that the optimal solution for these problems would be found among those points where lines are meeting. I mean, lines, if I'm drawing it in 2 dimensions, there will be like hyperplanes, like surfaces in higher dimensions. But on those points where those things are meeting, and in this case are those dots, there will be an optimal solution. And the solver will start in such a dot and move to another dot, which can be obtained by just doing one replacement of one of the line by another line. So in this case, this was at the point where I'm meeting the line x1 bigger or equal than 0 with the line x2 bigger or equal than 0. And now I'm meeting the line x2 bigger or equal than 0 with the line x1 less or equal than 1000. So by replacing the things that I am actually intersecting over there, I can move from one initial solution to a better solution, and then to a better solution, and then to a better solution, until no improvement can be found. And that's exactly what the computer is doing, regardless of whether we can draw it or not. We can do the mathematics of this algorithm regardless of having 2 or more variables. That is not the problem. So the mathematics will work, and it will stop improving on the point that cannot be improved any further, like an optimal solution.
Sorry, could I ask you something, Joaquim?
Sure.
So if you're depicting the algorithm like that there in your previous slide,
yes,
then that's going to be a local optimum that it finds, not necessarily global, right?
It's going to be global due to mathematical properties of the problem. Because it's linear optimization, it's going to be global. And it's also global if the functions are not straight, like linear functions, but if they have the proper curvature. See,
yeah, okay.
So if I have like convex functions that I'm minimizing, so it's gonna. So indeed, the Karush-Tucker conditions tell you about local guarantees of optimality, and then you need properties of the model to translate them into global optimality conditions.
Okay, so you're saying in this case, because I have hyperplanes, I actually get a global.
Yeah, yes, okay. That's completely true. And now this Mr. Danzig invented the algorithm. He also contributed to the first implementation. He was also coding it. It all happened during the Second World War, so it was all very secret. The first thing that was reported, it was after the Second World War. And then we learned that in the year of 1947, the same code in the computer that was used by then could solve a problem with 9 constraints, 77 variables, in, can you guess how long? Unmute and tell me how long it took in your guess. Anyone there? Well, the computer was old. Oh, somebody said 4 days. Okay. Well, it took about a day, more or less. Well, the computer happened to be like a big room full of electronics. It was called the ENIAC. It was indeed a room full of electronics. It's also the birthplace of the term bug, because the computer was running except if a bug would collide with a cathodic tube and the whole thing would short circuit. So people did not make software mistakes by then. There were only bugs committing suicide. But it took about 1 day to solve this problem. And now you can wonder what happened in the meanwhile with the computers. Well, the computers got better, of course. And this table is not starting in 1947, it's starting in 1985 for a simple reason. In 1985, the company Sun was producing workstations that could be bought by companies. So the Sun 3150 was a machine that you could order and buy. It was not the case for the ENIAC, there was one of a kind. And then we can come closer to today.
a machine like the laptop I'm using to tell you these stories. And if you have like the same instance of a problem to solve and the same code running on these different machines, then the power of the hardware improvement can be seen as almost 18,000 times improvement in terms of speed. So the problem being solved now is a little bit bigger. It's a problem of scheduling pilots in some way, with 1141 constraints and that many variables, and solving that instance with the same code on these machines. It went all the way from this amount of time to about 2.5 seconds. And you can tell, okay, I just need to wait that the hardware gets faster and all my problems are solved. Well, fortunately, it's not only the hardware that is improving, also the software, or let's call it the algorithms, are improving. And that analysis that I showed on the previous slide were done by this gentleman. This gentleman is responsible for two of the biggest, most important solvers that we can find nowadays. He implemented first Cplex, and then he moved to another company that he created and implemented Grobi. Those names will become very important to you if you are doing mathematical optimization. In my opinion, Grobi is the best solver that you have for linear optimization right now. And then there were also other improvements that came from mathematics by noticing that if you have such a feasible set, and I'm drawing here one in 3 dimensions, it looks like a diamond. You have all these hyperplanes in delimiting the set, and you have all these intersection lines, intersection points. You can see that the method of Danzig, the method of simplex, would probably take very long paths to go from one initial solution to another one. So what happened is that people also realize that you can go through the interior of these sets, and that may get you to the optimal solution much faster. And in fact, this was the gentleman that implemented the first practical interior point method for linear optimization back in the 1950s. No, sorry, he was born back in the 1950s. The method was implemented in the 80s. All right, so hardware gave us what we can estimate as a 17,500 speed up. And there was a speed up of roughly 20,000 times from mathematics. This is the combined speed up. And nowadays, if you can input such problems into a computer, you can solve them. So this, you can consider linear optimization to be a very well dealt with mathematical optimization thing. It's very easy to solve nowadays. And then you also get this notebook of Caroline to play with. And it's here. It tells you the same story. It tells you about Paiomo and the solvers it supports. Oh, this is not the right one. I will give you after the break the right one. This is the one I would send my students to have a short break and implement the solution. And I will fix it, and I will give you the PDF with the notebook that answers the question, not the notebook that asks the question. And before I send you to a break, let's just proceed and tell you about this. Alongside with the Paiomo book that I already referred to, there is also this book where I am one of the authors of. And this book tells you how to do mathematical optimization in a very hands-on way, not only in the linear case, the mixed integer linear case that we will cover later on slightly, but many other different paradigms of optimization, including optimization that deal with uncertainty, because most of the times we don't know for sure that indeed a trophy takes 4 decimeters of wood, or it will yield 12 euros of profit. There is uncertainty in the data, and also that can be dealt with. There are many ways of doing that. And what you see here is something that is free. This is what we call the online companion to the book. There are many examples here. They all consist of notebooks that you can deploy by pressing this rocket, and then you open the notebook in your own Colab. And this story of the microchip production problem is actually the same story as I told you with Caroline, but then with different ingredients, because we thought that we should not have very childish stories on our books, that's all. So you can find these and much more on on the thing, and the book itself is being finalized right now. So it's going to be printed by a publishing house, but this will stay there free forever. So you can use this to your advantage as much as you want. I will suggest that we have a 5-minute break now. I will make sure that during the break, I will fix the link to the Caroline notebook to include the one with the solution for you to play with. And I will also produce a PDF of the slide deck. And I will ask Marta to put that PDF on a point that you can access. So for the second part, you will be able to click along with links from the PDF, and you can save it for your future reference. After the break, which I suggest we spend 5 minutes on, we will proceed understanding how mathematical optimization tells us how far it is from a point to another, which gets us closer to what Parvati and Brit already explained you about pizza and about accessibility metrics. And then we will have another break. And after that second break, I will tell you 2 stories about 2 projects of ABW that have been done, and they use mathematical optimization. Then you will be able to understand how that all works. Okay? So let's agree that we see each other in 5 minutes. Let's round that up a little bit. So it's now 33 on my clock. Let's say 40. Can we meet at 40? All right. Let's meet at 40. And in the meanwhile, I will do what I promised you to do. See you. right. So I think it's the time that we have agreed to be back. In the meanwhile, I did add the link to the resolution of Caroline, which, as I said, matches that BEAM example of the online hands-on book. Of course, that it's slightly different there because it's a story of Caroline, but you may also find some different things. The one of Caroline gives you different versions of a possible resolution, and the different versions aim at telling you how to acquire the data from things like pandas, data frames, and to get your optimization part of your solution more aligned with your data part of your solution. So you may find all that. And where can you find it? Well, I also sent a PDF just now to Marta. So Marta is very busy, probably reading her email and making sure that the PDF is shared with you. It's all very done right now. So I think that in the meanwhile, those things will all materialize on your side. And let's proceed with the part of the story that I want to tell you after the break. So as I said, the second part will deal with finding distances and travel times. Distances and travel times were probably already mentioned to you as being very important things to be able to compute in order to decide about what is the accessibility that people face in terms of things that are important to them. Those things could be, for instance, hospitals or any other type of health suppliers or any other things that are important. But it's also for us important even in our mundane lives. We want to be at Amsterdam Business School for some reason, like to have a meeting with the other fellows, and you want to find, well, how to get there, or you just want to find how to get to some place that you need to visit. Nowadays, we can all resort to our telephones, which run apps that can tell you right away how to get there. But what I want is to demystify a little bit what is happening inside those apps or inside the computer, or how can a computer actually tell you how to get to one place, from one place to another, and how long that it's going to be both in distance and in time. So that's what I want to cover now. Before I proceed, are there any questions from your side? As I said, just a mute, tell me. Everybody's silent, so let's go. So in fact, all these things that those beautiful apps tell you right away how to go from one place to another, all this magic is still mathematics. And it's also a mathematics as a form of abstraction of a reality. And the reality could be, if I'm looking to part of the Netherlands from above, I will see those areas, those greens, those browns, those blues. And if I am adding a little bit more information to reality, then I would imagine those labels that give me names of cities, maybe even those labels alongside with lines that are roads, but this is still very close to reality. That's not what computers use. Computers need to bring this reality into the form of a mathematical model. And our path from reality to that mathematical model involves raising a little bit the abstraction. And the very first step by raising the abstraction from this, what is part of the Netherlands, to what is going to become a useful mathematical model, could be just forgetting the country, forgetting the landscape, and having like a map. So this is the first simplification that you can think about. And if any people on this meeting is as old as I am, then you have navigated with maps yourself before all these technologies became commonplace. I'm used to, in my past, I was used to actually having to acquire a map for the region I wanted to travel and to try to find my path on those lines on the map. But that's not what computers do. Computers go even one abstraction level higher than the map, and they replace the country and all this information by just a collection of points and lines. What we are looking at is what mathematicians call the graph
or a network if the graph includes also some weights that tell you what is the length of such a line. And if you also have information about whether you can go on that line from one node to the other node or also back, this type of information is also what characterizes a graph being called a network. So in fact, computers deal with infrastructure that enables you to travel in terms of graphs, and graphs look like this. You can still imagine that the Netherlands is being drawn here, but what we see here are all the physical segments that can be traveled either by car or walking or by bike. So those are the segments that connect points and allow you to traverse those segments with some modality, the modality being a car or a bicycle or whatever. And it becomes like a drawing like this. And once you have a graph, then you can apply the power of mathematics on it. So if this is a very simple graph, which is of course much smaller than this, and this is even smaller than the whole of Europe, this is just part of the Netherlands, you can imagine that what your favorite navigation app is doing is dealing with very big graphs. So I have here a very small one, with just like 1, 2, 3, 4, 5 nodes. Those are the points. And I have a number of edges or arcs. Sometimes they are called arcs if they have an orientation. So I have one that goes from A to B, and it has a length of 10. One that goes from B to C, it has a length of 1. So I have like a very simple graph. And in this graph, I want to find the fastest way of going from A to C. If what is here are traversing times, if it says it takes 10 units of time of going from A to B, then it's the fastest way. If it says that it has a length of 10 in terms of physical length, then it is the shortest way. But the algorithm itself is always called shortest path, regardless on whether you are minimizing time or distances or any other thing of interest. But what you want is to find the path. What is the path? The path is a collection of lines that are connected and bring you from a node where you are to the node where you want to be. I mean that the lines are connected because they bring you from node to node in a sequence of movements that only use lines that are in the graph. So for instance, I can go from A to C by going from A to B with a length of 10, and then from B to C with a length of 1, and I have a total length of 11. I could also go from A to D, and then from D to C with a length of 5 plus 9 is 14. So far I would prefer 11 because it's shorter. But I want to have the fastest and the proven fastest. Unfortunately, we know how to do it. And now I can even tell you, you will learn 2 ways, because I will not explain in detail, but this is also a linear optimization problem. You could also model it with an objective function with constraints and solve it with a solver via Pyomo. You could, but it is a very special case. And for this special case, there is a dedicated algorithm that solves this problem directly on a graph. And it has been invented by a mathematician called Dijkstra. We will see it, but you can also, this was meant to be an add-on, but I'm talking for so slowly that I will not send you on an add-on anymore. You can also actually do it with a dedicated package in the Python ecosystem, which is called Network X, which includes indeed an algorithm to compute shortest paths. And the aim of this hands-on would say, okay, see this example, which is very small with this small graph, modify it to include this graph and find the shortest path with Network X. And then I would proceed and tell you how Network X is working. That's what I'm going to do now. So Mr. Dijkstra found a method to compute shortest paths, which guarantees to find the optimal solution If there are no negative numbers involved, well, and you will say, well, that's kind of safe if it is travel time and travel distance, because you cannot go back in time and you cannot go back in distance traveled. But graphs are mathematical concepts that can be used to model many different things. So there are graphs of interest which have negative numbers, but they cannot be dealt with by the method of Dijkstra. The method of Dijkstra is based on a very simple observation, which once translated into a mathematical truth becomes a theorem. And the very simple observation is the following. If you are trying to find the shortest path from your home to the Amsterdam Business School, well, it can be a very long path if you are located in another country, for instance. But let's just imagine that if you are indeed finding the shortest path from your home to the Amsterdam Business School, and if you notice that that path actually goes past your favorite restaurant, then you already know two shortest paths. The shortest path from your home to your favorite restaurant, and the shortest path from the restaurant to the Amsterdam Business School. And why? Because if you could replace any of those two by a shorter one, then you would have a shorter path to reach your final destination, the Amsterdam Business School, by concatenating those two. So not only we have here already a statement, we also sketched the mathematical proof, and that's behind why this algorithm actually really finds the shortest path on a graph without negative numbers. It works as follows. If you are at your point of departure, then you know that the shortest path to reach where you already are has the length of 0. That's kind of obvious. You are there already, so it takes 0 to get there. And then you examine what you can reach from that point. So you are at A. It takes the shortest path of 0 to reach A from A. And then you can say, okay, if I am at A, I can reach any of the nodes that has a direct connection from A. So that's, of course, B that can be reached in 10, and there is D that can be reached in 5. And then I update the information that was previously absent. So I had like no information about how can I reach B in the shortest possible way from A. And the same for D, actually for no nodes except for A. And then I update it to reflect the best known length so far. So it was nothing became 10, it was nothing became 5. So what is the 10 is 0 plus 10, what is the 5 is 0 plus 5. And now, because of the theorem that we just proved about the shortest path is concatenating, we know that the lowest of all these informations, the lowest of all these numbers can never be lowered. So I can say, full of certainty, that this D reflects the shortest way of reaching D from A, and it will be 5 and never be improved. So I can move there, and I can repeat my steps, and I can scan those that I can reach from D. Those happen to be B, C, and E, because there are lines from D to B, from D to C, and from D to E. I update, as I said, the information there, and from B, that was going from 10, the previous known path length, so that was from A to B, became 8. And why? Because 5 plus 3 is 8, and it's smaller than 10, and 5 plus 9 is 14, and it's smaller than knowing nothing, which you can actually replace by plus infinity if you like to have something to compare against. And then you have like 5 plus 2 is 7, which is again better than nothing. And again, these 3 numbers that are now 3, they were previously 2. The one of them is the lowest. It happens to be that 7. And from there I can repeat, and there will be a possibility to go back to a node that is now fixed. That's the A, so I don't care. And there is this node that is not yet fixed. And then I update what was there. It was 14. And it becomes 7 plus 6 is 13, which is lower than 14. Then it becomes indeed lower, 13. Then the lowest of these 2 is 8. And then from 8, I can update that one to become 9. And now I know that the shortest path from A to C has a length of 9. And you want to know the path. So it's actually very simple. You just go back from C with that information. So you know, okay, I can reach it from A in a total length of 9. And you just want to know, where did I came from? Well, you came from either
B because there is a line going from B to C, or from D because there is a line going from D to C, or from E because there is also a line going from E to C. But the one that you actually came from is the one for which 8 plus 1 is 9, or 5 plus 9 is 9, or 7 plus 6 is 9. Well, it happens to be 8 plus 1 is 9. Then you go back to the point that gave you that segment, that is the point B, and you repeat. So you either came from 0 plus 10 is 8, no, or from 5 plus 3 is 8, then you came from here, and then you repeat, and then you came from there. So basically you discover the path after you have the numbers by doing a very simple backtrack algorithm, and you find this path. So actually, Professor Dijkstra invented this many, many years ago. It is still the heart and soul of all these shortest path algorithms. And you may wonder, how does that actually translate into more complex queries? And before I move to answering that question, let me just ask you, did you get more or less an idea on how the computer is solving the shortest path on a graph? I guess so, as you know, rand's being reason. So, okay, the algorithm that I described is applied, and then there comes the shortest path, and you know from A to C, it was 9 in that case. So you know from London to Edinburgh is so much, and then you know from, I don't know, from Nairobi to somewhere else, it's also so much, and you can also compute that for any place for which you have indeed a graph describing the infrastructure that you can use. So what about the situation that you want to do some kind of distribution, like you order things online and they will be brought to your home, but before they are brought to your home, there is a route being designed for that transportation van. So imagine that you are one of the addresses in this hypothetical network that are numbered 1, 2, 3, 4, 5, 6, 7. And those are the ones that ordered something to be brought to their homes. And all the others, like on A, B, C, and so forth, did not order anything today. So they are not really important for the distribution that I want to organize, but those are. So now I want to actually find a route. And in order to find that route, I need to put these stops or these addresses that I need to visit in the proper sequence. In order to evaluate the different sequences, I actually need to know the distances in between each pair of them. So knowing the distances in between each pair of them is what Dijkstra can give you by finding the shortest path from 1 to 2, from 1 to 3, and so forth. And then you can move your attention to this smaller graph, which is now reflecting those stops that you need to visit. I said, like you order something online and you have a van that does all this, or you want to do some vaccination campaign and you want to be on all these different things, and you have a van that transports your medical stuff and your supplies, and you want to find the shortest possible route for those. So when you want to find shortest possible routes, you need to start with like the full matrix of interdistances between each pair of those possible locations. And you could say, okay, I just learned I can do it with Dijkstra. But after you do that, then you also, of course, you need to find the proper sequence, and that's another algorithm. You would say, okay, if I'm visiting predetermined addresses that never change, I can also pre-compute these. Like when I was navigating in the old days, my maps also included this type of matrices of this type of tables, telling me like the interdistance, the distance in between pairs of cities. But now you would say, okay, I cannot pre-compute these anymore, because if I am doing vaccinations, I can go to any village and I don't know which one to go tomorrow. Or if I'm doing distribution of things that were bought online, I can go to any address on a country or even in a continent, and that's not possible to pre-compute. And in order to tell you that it's not possible to pre-compute, think about the United States of America. It has like 30 millions of locations. This will never fit in a computer, let alone that it takes too long to pre-compute. So you'll say, okay, well, Dijkstra already solved the problem, so I can do this with Dijkstra. So what? Who cares? Well, but the algorithm of Dijkstra, as you have seen, is actually scanning a network like in all directions before eventually it hits the destination. So in this hypothetical question that I'm answering now, I should go from this place, which is somewhere in the city of Utrecht, to this place, which is somewhere in the city of Zoetermeer, and then my method of Dijkstra would do all these computations while it's only interested on the shortest path that connects these two. And how does this translate back to that question of finding routes? Suppose that you need to visit 10 cities, and if you have like a implementation of the method of Dijkstra that gives you one distance in a second. So if you want to have like a matrix of all the distances from each of the 10 origins to the 10 destinations, you would need to wait for 1 minute and 40 before you have information that will allow you to actually find the proper route. If you have like 5,000 potential addresses to visit, like for instance, a DHL or a FedEx, which is probably going to have on every day, it's going to take you almost 1 year before you can do the routing. So forget your next day delivery. So this is not the way that things are done nowadays. And you can also think, okay, that Dijkstra looks very clumsy, but it's also very handy because on this yellow thing, I found a lot of shortest paths. So I could do my whole matrix 1 row at a time. Well, you could, and then it would still wait for 3 hours more or less before you can do the routing. Well, fortunately, nowadays we have more advanced algorithms. And it was in 2008 when this gentleman wrote his PhD thesis in Karlsruhe, and he found actually the very first clever way of computing shortest paths on road networks. It's still based on Dijkstra, but the Dijkstra which was complemented by a pre-processing. The pre-processing was done upfront before you actually do the Dijkstra queries to know the shortest paths. And once that pre-processing is done, Dijkstra can move much faster. And that was discovered in his PhD work. And it placed him on the edition of 2008 of the Scientific American Top 50, which is a publication that comes every year. And it lists the 50 most influential individuals or institutions of that year. This means that he was among the 50 most important technology entities, and he was above Google and above Microsoft as a person. Well, that means that this was indeed impactful stuff. And just to tell you what that algorithm from 2008 would do with the same query of 5,000 times 5,000, it will take like 3 minutes to compute a full matrix of 5,000 pairs of shortest paths, distances, and travel times. All right. How does that actually work? It works like this. I'm now looking at a graph of a bit of the Netherlands. Now, this one is the central point, more or less, of this part of the graph is Amsterdam, and the Amsterdam Business School is somewhere around here. And if we are looking at this graph of Amsterdam with the eyes of Dijkstra, then all these lines are gray. I mean, all these segments have equal importance to the algorithm of Dijkstra. What this gentleman, Dominique Schultes, realized is that not all these segments are equally important. There are segments that are more important than others if your path is long enough. If your path is long enough, you will end up resorting to only a subset of these segments to take you really far. And you will say, okay, this looks like a classical map with things like highways, motorways. Well, the resemblance is striking, but the colors were given by an algorithm based on solid mathematics and not given by the classification of your local municipality. Indeed, it happens, if the highways were well designed, that they are really important, and then they get the right color. But this is given by mathematics. And once you have done this pre-processing, which is basically coloring your map, then you can do the Dijkstra queries in a different way. You can see in this animation that some of the edges are becoming colored. There is a kind of a blue color that is emerging over there. And it's starting very slowly because in the beginning of the process of finding the shortest path, there are many edges of seemingly equal importance. But then at some point, apparently I stopped the animation. That's also part of the problem. I was touching my mouth and then things stopped. At some point, this process of labeling these nodes will end up reaching a
group of edges, which belongs to this other color, this higher hierarchical level, and it takes you very far, very fast. And if you do it from both the origin and the destination simultaneously, this is what happens if you do it from the origin side. If you do it simultaneously, then you see that these two queries will meet somewhere, and then the path will be discovered by just mixing the results of those two queries in the proper way. And this algorithm is, of course, a more sophisticated implementation of what, in fact, is the idea of Dijkstra, but then based on this pre-processed map, which classifies the edges in these different levels of importance, as the callers were explaining. And then, as you may witness, in order to find a path like this, far not all the edges were scanned, which means that there is a huge speed up here, and the optimality is guaranteed. So the importance of being able to find distances using the infrastructure can be illustrated by many of such graphs and many of such drawings, and you may have seen drawings like this in the presentation of Parvati, I'm pretty sure. So what I'm looking here is a point in the world. It happens to be an hospital in Nepal. Nepal has a very challenging geography, as you may imagine, with the Himalayas and everything. And what we have here is the difference between what would be your perception of accessibility if your metric was just like the bird's metric of the Euclidean distance. So the circle with this yellow perimeter is like 10 kilometers from this hospital, and you say, okay, everybody in that 10-kilometer circle is within 10-kilometer accessibility of my hospital. But you, of course, you are misled because of the geography of the country, because of the infrastructure that is present there. Then you realize that those that are in the brown area are able to travel 10 kilometers to reach the hospital. And those that are only on the green area are those that can take up to, up to 1 hour walking before they reach the hospital. So the reality can be much more different than what you will do if you just do like a rough approximation of having the Euclidean distance between 2 points in the world. This is the importance of doing your shortest path computations based on real infrastructure data, like can be provided by OpenStreetMaps or anything else, and a proper algorithm on top of it. So I think that this is what I wanted to tell you before the second break. And I'm giving you a lot of gifts with every piece of thing in this training. And this little notebook is actually telling you a bit of history about all these people that contributed to shortest path as being really scalable nowadays, including Dominic Schultes that I have mentioned before, a bit of Python to also do visualization of things, and a lot of Python to do computations of things, and also Python to extract like a graph of Amsterdam. This builds on top of what you already got from Brit and what you already got from Parvati as an explanation of pizza, but it's standalone. This is not using pizza, so this notebook will run on your browser from the beginning to the end, and it will enable you to compute like the shortest path from the central station of Amsterdam to the Amsterdam Business School and whatever, and many other things. It tells you how to do geocoding and everything. And it's probably a little bit of a duplicate with what you already had from Brit and from Parvati, but it's a story that complements my teaching on the algorithm of Dijkstra and follow up from there. So now we have the moment that I will call for the second break, because after the second break, I will tell you about two of the projects that the Analytics for a Better World Institute has conducted. One of them related to the strategic development goal of no poverty and zero hunger, which is the story about an app that can be used nowadays by farmers everywhere in the world to optimize their cattle feed. And I will tell you how that becomes a mathematical optimization problem and how that is solved. There is also a notebook telling you that same story. And another one relates to health for everybody by deciding where to put hospitals in a very well chosen place
in a country like Timor-Leste, and there will be a notebook that will focus on one of the provinces of Timor-Leste to have like a amenable data, and that you can redo these things with mathematical optimization. So this is what I want to cover after the break. I see that we are now at 4:10. If that would be okay with you, we meet at 15 past, within 5 minutes. Before we say goodbye for this second break, I would like to ask you if you have any question, any striking question on the things that were addressed before. No. So I will not take any more seconds from your break. Let's meet at 15 past the hour. And at 15 past the hour, we proceed, and we are going to see how these things are done with mathematical optimization. See you. Those that prefer to have the meeting with your computer, if you want to chat, it's okay. You don't have to, but if you want, it's okay. Well, I'm just going to open a few notebooks, so I'm not yet proceeding. It's still break, but I will just be opening some notebooks to have things ready a little bit ready. That's all what I'm doing. All right. So it was a short break. This is the time that we have agreed to restart and to go towards our third and last part of today, at least what I intended to tell you today. So what I said that we would be doing is that we will look into two of the projects that the Analytics for a Better World Institute has conducted in the past, projects that have led to some things that already exist. In particular, this first one has led to an app that you can install on your own smartphone. And the app is actually free. You do not need to pay because there are some sponsors that pay all the costs. And what you can do with such an app is you can actually feed the characteristics of your cattle, and you can feed into the app the available ingredients that you can find, that you can buy, and the price that you may pay for those ingredients. The app includes all the domain knowledge that translates into telling, let's say, the model that will need to be solved. What are the nutrient requirements of that specific cattle? Suppose you have chicken, you have pigs, you have ducks, whatever. So this cattle requires a balanced diet with a minimal amount of some nutrients, a maximal amount of some other nutrients, and things like that. That domain knowledge is part of the model and part of, let's say, data that is already available to the app. The other data you provide, and that regards your situation, the situation which is around you, like what ingredients can you buy for what price, and how many chickens do you have, and these type of things. And then the app will tell you what to buy, how much of it to buy, and how to combine those ingredients in a feed that will be healthy for your cattle. And the implementation of this app in the smartphone makes it quite, let's say, insensitive to connectivity issues. It may be that you are in a very, let's say, in a very remote area with poor internet. So you can indeed input some things while you have internet or not, but you may be on the field, and if you want to do queries and to ask the app, what shall I buy and for how much, everything is done on your phone alone. So all the technology needed to solve this, including the solver, is implemented in the app. Which indeed, I think it's quite amazing to see that this type of mathematical optimization methodologies can be so portable as to be completely implemented in your phone nowadays. Of course, that you could say, well, who needs that? Because I can always resort to servers, like when I do my query for the shortest path. I know that a company like Google is probably running a server somewhere and telling me the answer. But as I said, there are areas in the globe with very poor connectivity, and some of the users of this app are located in such areas. Okay, but what is this all about? So we open this notebook. I had already opened it, so it's already here. And what I can tell you about this notebook is that it is one of the assignments that we give to our bachelor students on a course called Analytics for a Better World, where they actually learn this type of methodologies, having an objective that relates to one of the projects that we have done with the proper sustainable development goal being identified as well. So the data at hand is data like this one. You can see here a table that tells you about the available ingredients, the price that you pay, and then what is the amount of different nutrients on that ingredient that are important for your cattle. In fact, you are not managing this data as user of the app. The only thing you need is to identify by the common name the ingredients that are available to you and the price that you need to pay. The remaining part of the data has been obtained by nutritionists and a lot of experts that have done this decomposition of your ingredient into nutrients. And then there are also things like let's go back here. The data, that's the data that we pass to your students. Let's go back here. The data that we pass to our students includes like an ingredient database, the nutrient rules and ingredient rules. All this is, as I said, domain knowledge. And the only thing that you control is what are the ingredients available to you by what price. So, for instance, the ingredients table has more information than the one I've seen before, because it also tells whether the ingredient is available or not, and then the price and all these things. There is also the nutrient rules table that tells that for the cattle at hand, so that could be like a chicken or whatever, specific nutrients should have like a lower bound and an upper bound that should be met in the feed. So this is for a specific type of cattle. So for instance, this nutrient, which is an acronym for something which I do not know at this moment what it means, but for instance, if I scroll down, I may recognize some things like calcium or natrium. They should be calcium between 7 and 9, natrium between this and this, and these are the rules that you need to obey in your feed to make it healthy for the cattle at hand. And then there are also some rules about the ingredients, which, for instance, tell you, this is part of an Excel notebook, and it tells you that, it's hard to see it here, but it tells you that you should not combine that many ingredients of this type in order to have something that you really want to feed your cattle. But this is data. Once you have read the data, then you can treat your data. And when we give this assignment to our students, it has several steps, including translating your data to useful information, like from the data, collect the nutrient bounds. This is the part of the Python that will yield the nutrient bounds translated for all the nutrients that are interesting for you, and the ingredient bounds and so forth. And they have done this in first steps of their assignments. Then they also extract the combined ingredient rules, which was that funny table that I was showing to you, which indeed translates to saying things like this nutrient plus this nutrient, sorry, this ingredient plus this ingredient plus this ingredient plus this ingredient should be at most that much. And then you get to your mathematical optimization model. And the mathematical optimization model is now building on the knowledge that I gave you today. And it is a little bit of, let's say, a more sophisticated model because of all these strange symbols right here, which is the way mathematicians like to tell that something should hold for every thing of this type. And then you are dealing with a set of the available ingredients. That's an abstraction for like the cotton and the sunseed flowers and all those type of things that were available to you as ingredients. This abstraction is that I collect all of those in this set I. The nutrients that I need to respect in my feed are collected in this set N. And then there are also those combined ingredient rules, like these examples, that like fish and that type of fish should not exceed 0.07. These combined ingredient rules are these. And then if I have also information like the cost of each ingredient, which is of course very important for these farmers, because they want to have like the cheapest feed for their cattle, which is indeed healthy for the cattle. So the healthy part are the constraints, and the cost relates to the objective function, and the decision variables that they actually have is how much of each ingredient to put in the mix. So there will be ingredients that will not be used. So this variable xi will be 0. And for some ingredients, there will be a proportion of the kilo. Like they want to produce a kilo, how much in that kilo will be of each ingredient. So these are the decision variables, which translate to how much should they buy. And then they want to pay like the total amount of money
which is the lowest possible for the ingredients they buy, and they need to respect that, like the nutrient rules, because the ingredients translate into nutrients by that table that I've shown you, with the proportion of the ingredient that is like natrium, calcium, and all that stuff. And there are all the lower bounds and the upper bounds for those nutrients on an healthy feed. There are also lower and upper bounds for the ingredient itself on an healthy feed, the combined ingredient rules, and then a constraint that tells you that all these decision variables, one per ingredient, are actually decomposing the feed into parts. So the total feed is one, and the sum of the parts is that decomposition of the total feed into parts of the feed that are expressed for some individual ingredient, and you should only use non-negative parts of your feed that translate to each of the ingredients. So if this is the model, then this is like the Payomo translation of that model, and it has like more sophisticated things because we need to deal with these abstractions. Like I have a collection of nutrients, a collection of ingredients. So this is a little bit more sophisticated than the example of Caroline, where we write like 12 for the number of the coefficient of the price of a trophy of type football. Now I don't have a number 12, I have like a CA and a CI, which is indexed on the set of ingredients. So all these things are the way that we tell Payomo that I have a set of ingredients, that I have a set of nutrients and a set of combined rules. And then I will end up declaring my variables, and I have all these parameters, which are actually numbers that are acquired from a data frame. And if you see the resolution of Caroline, there will be 4 different versions, and one of them is closer to this because it's dealing with data from a data frame. You have your decision variables, your objective to minimize the sum of the costs. You have like the translation of the nutrients into, the ingredients into the nutrients, which is this expression here, and all the constraints that actually implement this mathematical model. And once you have this, you can actually just ask the model to describe part of the constituents. These are just decision variables, the x's. And I see that I have one for barley, one for blood of low quality, one for bone something, and I have all these ingredients. And then I see that my variables are limited by some bounds, sometimes both a lower and an upper bound, sometimes only a lower bound because there is no meaningful upper bound and things like that. So I can examine my model, and what I can also do is to vary the data that I feed to my model and see how that translates to the model itself, because now I have like 2 different lists of ingredients, like all the ingredients in my database on only those ingredients that were actually listed to be available. And then I see that indeed my decision variables will be different. I have here upper bounds that are never 0 because all the ingredients are available. And if I only use the available ingredients, some of the ingredients will be bounded to be between 0 and 0, meaning that that decision variable is in fact fixed at 0, meaning that it will not be part of my solution. And then what we see here is that I can solve the problem for different instances of the data, like assuming that that I can only use the available ingredients. I will have this feed, so much of cotton, so much of fish, and so forth, with this price per kilo. I also have some code that makes it more tidy, so I can put it in a data frame. And if I have a data frame, I can also ask the data frame to plot like a pie chart of the feed mix, and it looks visually maybe more informative. And I can do that for the case of all ingredients, the case of only the available ingredients. I can see that if I have all the ingredients available to me, I can get a cheaper total price than if I only have some available to me. That makes sense because I'm more constrained in the case that I have less ingredients available. But you can see that the model is actually able of making a different mix with different choices
but a price that is slightly higher, but not that much higher. And then you can play and you can go here and modify your list of available ingredients by saying, okay, I don't want any fish, I don't want any bones, or I don't want any seeds, and I get a different feed with a slightly higher price, and so forth. So you can play with this notebook. There is also some code here that can also put your feed into an Excel, or if you are writing a report and use LaTeX for it, my students do, you can also put this table into a bit of LaTeX, and you can also download your picture, which is your pie chart. So this is just an example of the type of things that our students at the university learn to do with problems that relate to strategic development goals, in this case, the story of the optimal cattle feed. But for you, what is, I think, important is to go back to the first part of the training and see how the model described here relates to the concepts that you have learned. You have learned that the mathematical optimization problem consists of decision variables, and in this case is how much of each ingredient will be in my feed. There will be an objective function, which in this case is the total cost of the ingredients that I acquire. There will be an aim for the objective function, which is in this case to minimize the total cost of my feed. There will be constraints. The constraints are expressed in the same decision variables, and they relate sometimes to upper bounds, sometimes to lower bounds on some expressions. So this expression extracts the nutritional value of my feed from the composition of its ingredients to each of the nutrients. So there will be a constraint for each nutrient. So this row is repeated for each of the nutrients that I have in my database. And then this row is repeated for each of the ingredients that I have available. And then I have also some additional rules that say that some ingredients in the totality should not exceed some kind of upper bound. And then I have these more or less technological constraints that tell me that my modeling decision was to model the proportion or the part of my feed of each ingredient. That's why it should add to 1, in the same way as a pie chart describes a whole. So all these adds to 1. And they should be bigger or equal than 0, meaning that some of them are actually 0. And you can also see that when you solve it for different available ingredients, you get different choices because all the other ones remain 0. And you may notice that this is, of course, of value. Those farmers that use it are extremely happy to have this instrument, and it is just linear optimization. So it is just that model, like the model of Caroline, with linear constraints, linear objective functions, and continuous decision variables. And this is that part of mathematical optimization that I have told you that is so well solved that nowadays, if you can input such a problem, the computer will always solve it for you. Okay. So a very simple example of mathematical optimization, maybe in its simplest form, the so-called linear optimization models with a very high impact. And this notebook tells you how this optimal cattle feed is actually modeled in a mathematical optimization problem. It provides you with relevant data and gives you the ability to play a little bit with it. Okay. So this was my first of 2 stories that I have selected to tell you to conclude today's training with illustrations of mathematical optimization in action for projects that the ABW has applied. Before we proceed to the second and last one, which involves things about accessibility and decisions where to put services, before we proceed there, let me ask you whether you have any questions so far. Are there any questions so far?
There's one question from the chat. Does
Mark,
any...
Yes?
Oh,
Mark,
well, it's, I would say it's more for everybody, but do anyone from the cohort did their project using mathematical optimization? I would say maybe from last year Yeah, from last year. I can get back to you with that answer because I'm not sure, but we can ask the organizers of last year.
Okay. But talking about just this session today with you, are there any questions about what I told so far? No. In that case, let us proceed. So the second example concerns the country of East Timor, Timor-Leste in Portuguese, one of the old Portuguese colonies. It's situated, as you can see here, at the north of Australia, close to the islands of Indonesia. Actually, Indonesia many times wanted to claim Timor-Leste as being part of their own country. And it's that part of that island plus that other part there. So this red area here is Timor-Leste. And Timor-Leste is indeed, consists of this collection of provinces. And it's a country with also a very challenging geography, not for the same reasons as Nepal, but for the fact that the infrastructure of the country is very vulnerable. So there are many roads that are just mud roads, which wash away in the rainy season and everything. And then there are, of course, points where people can have health care. They exist. Those are the red dots already on the map. And one of the aims of the project was to assess what is the true coverage of those points, what is the true accessibility of the population, how many of those inhabitants of Timor-Leste are within some threshold, like for instance, like 30 minutes driving or 1 hour walking or 5 kilometers walking distance from healthcare. There is this strategic development goal that a huge amount of the Earth population should be within 5 kilometers of an healthcare. Well, of course, that you may know by now that the reality as we know it now is dreadful. There is a huge amount of the Earth population that it's not at all at that distance of an healthcare point. And for Timor-Leste, we did this study, which was done together with the World Bank and has resulted in an advice that was taken in the public expenditure of the country, which probably will lead to implementation along what we advise, and what we advise is based on mathematical optimization. Again, there is this notebook, and this notebook again relates to a project that our students do during their studies. It's a simplification of the data of the country. So the data that we give them is just one of the provinces, the province of Ermera. And the province of Ermera, if I'm not completely mistaken, is, I think, this one here. So you can see that the shape of this region where my mouth is waving around is more or less replicated in this map. So the map is very stylized. The students get coordinates, the students get points, get numbers, and they do not get really the need of plotting these on beautiful maps like with the volume package that you probably already have seen in action. They only have like very stylized data. They also get the distances between each of the population points. So the population points are here depicted at those gray areas. So there are individual points, and some points together become those areas. And those squares, the blue squares, are the potential locations for an hospital. And the question that they need to answer is, suppose that you have a budget of only 5 hospitals that you can build, which one should you take in such a way that the population within a threshold, and I think it was a threshold of 3 kilometers, I think it's probably on the slide. No, within 5 kilometers, with a threshold of being at within 5 kilometers of one installed hospital, and you want to maximize the total weight of the population that becomes reachable by that threshold. Well, if I scroll all the way down then you see that the solution will look like this. And you see that there are, in this specific case, population in areas that will not be served, but that's because you had a very limited budget, but still the choices made are such that it's not possible with that budget to serve more people. And I can see that in this case, it was solved for 3 kilometers threshold and 5 hospitals. But let's go back. So what my students had as a question in order to learn mathematical optimization, they were asked to compare 2 different models. Because I'm going to tell you this now, I did not tell before, the art of translating like a story, a reality, to a mathematical model does not lead to a unique solution. There may be many ways to model the same reality in a correct way with a mathematical model. And then it happens that these models do not always behave the same way. And when I mean behave, I mean the effort that they require to be solved. We are now talking about a type of mathematical optimization which is harder to solve than just linear optimization with linear functions and continuous decision variables. We are talking about a type of mathematical optimization that may include very difficult problems to solve by a computer in a reasonable amount of time. And then the model that you choose influences the time that you wait, even if they all guarantee to find a correct, and of course then it will be the same optimal solution. So in this case, and I'm going to just briefly explain what happens, there are at least 2 ideas that you can use to model this problem. One idea is to see the decision where to build an hospital as a collection of variables that I call here xj, and the j's are the possible locations for the hospitals, which are all these blue squares. Each of these blue squares is one of those j's. And then there is a variable x, that indicates whether an hospital is built. And that nature of indicating whether an hospital is built translates into the nature of the variable being one variable that only takes 2 values, the value 1 and 0. And this is the deviation from the linear optimization paradigm that I explained before. So the linear optimization part is reflected in the objective function. In the constraints, I have only linear things, but then I have variables that are not only big or equal than 0, they also have like discrete choices, and that makes the problem much more difficult. That's what we call mixed integral linear optimization, which is more difficult to solve in general. But this model actually says whether I build an hospital and whether that specific person, customer or person or household located on each of the I household places, those are the gray dots, is indeed served at that location j, yes or no. So this variable will take the value 1 if that person can go to that hospital, and then the model guarantees that the person can only go to an hospital if the hospital is installed, is indeed open. So there is this relationship between the y variables and the x variables. And if we read it carefully, we will understand, and I will try to help you understand this in a minute. There are also constraints that deal with things like the budget. So I see here that I can only install up to P hospitals. So the sum of all the hospital indicators or hospital decision variables cannot exceed P. And since they are either 0 or 1, I'm actually counting the number of hospitals that I install, and I have a budget of P. I can see here that this constraint is telling to each of those persons on a location I that they will be served by at most 1 hospital. So they make a choice, but sometimes they have no choice. So that's why it's less or equal than 1. And here I go back to this one. It says that indeed persons can only go to an hospital if it is open. So if the hospital is not open, then the variable xj takes the value 0,
and then therefore this n times xj is 0, and then the sum of all the yj's for that j is also 0, meaning that nobody, no single I, can go to that j. If the j is 1, or the xj is 1, and this n is actually the number of the number of the population count, then everybody can go to that hospital, meaning that this sum is actually bounded by something redundant, and then everybody can go there, and all those y's can go to 1. And what I want is to maximize the part of the population that is actually served. So I want to maximize the weight, and then this vi is like the weight of that population point, and sometimes it's just like the head count of that specific household. So this model relates to what I want to achieve. I only need to take care of one single detail, which is to say that those individuals at a distance bigger than the threshold from a specific hospital will not be served because they are too far away. So there are two reasons not to be served. One is there is no hospital, and the other one is I am too far, I am further than the 5 kilometers threshold that I want to meet. So this is what the model looks like in this case. And then the students also learn that they can model it in a different way. And both models, as I said, are equivalent in the sense that they describe the same reality in an accurate way. Therefore, also the optimal solution should be exactly the same, but this model is expressed in a different way. To start with, the decision variables, they don't have double indices. And if you are able to read these mathematical symbols, you already get the feeling that I have here many more variables in the first model. I have one variable per hospital, okay? Then I have one variable per household hospital. So there is here like a table of variables, like each row is a household and each column is a potential hospital. So there are many variables here, and there are less variables here. So I have here one variable per household and one variable per hospital. It already looks much attractive in terms of that, because there are much less decision variables to consider. And then the model itself looks smaller, but the model may require a little bit more of thinking to understand. I'm still maximizing the total weight of the population served, because actually Z says whether population I is served or not. I'm also still respecting my budget. I can only open up to P hospitals. And then I have the rest of the story in these constraints. And the rest of the story in these constraints may require a little bit of thought in order to understand, but once you understand it, it becomes, I think, really obvious what I'm saying here. I'm saying here that each person on household I, that's the ZI, which says, I'm not describing those variables here. No, unfortunately not. Each variable Z, oh, it says here, each variable ZI says whether that household can be served by an hospital that is opened. And then what this constraint says is that I can go to any hospital open, provided that it is within my threshold. So I don't care which hospital I go to, therefore I can go to any, and any is expressed like summing all of them. So if there is nothing, then this sum is 0. If there is at least 1, then this sum is 1. If there are at least 2, then this sum is 2. And I can only consider as potential hospitals to go those that are close enough. And therefore, these constraints capture the rest of the rules.
Could I ask a question?
Sure.
Are you also considering capacity of hospitals? Like a hospital can at most serve this many people?
That's a very, very good question. And these simple models are not considering that. These simple models assume that if the hospital is installed, it can serve everybody that seeks help at that hospital. Of course, that the question is very relevant, meaning that we also need more sophisticated models in such cases. Absolutely true. But what I'm doing is I'm only comparing two different models for the same simpler situation, no capacity, also no differentiation of services. So each hospital is considered to be fully equivalent to any other hospital. So it's a very simple model. But there are a very simple problem, but there are two different models being compared. And what I want you to remember at the end of this notebook is that I'm using here two different solvers, and I am comparing model 1 with model 2 with the data set at hand. I see that the objective function value is always the same, which indeed shows that the models are in that sense correct. They find the same optimal solution. Difference being that model 1 requires about 20 seconds to instantiate. That's actually the process of creating the mathematical model in Pyomo from the data set. It requires about 8.5 seconds to solve by two different solvers. They actually agree in the effort they take and in the optimal solution, of course. If I use model 2, the model requires less time to instantiate. Well, it makes sense. I have much less decision variables. I have much less constraints because it's all much more compact. But the solving times, that's where the striking difference is. I take about, let's say, 0.2 seconds at most to solve with this solver, and even less to solve with this solver and find the same optimal solution. So the bottom line from this learning is learning mathematical optimization is an exciting journey that probably never ends. You can always do better. It's good to take it seriously. It's good to consider it as part of your decision process. It's good to involve people in your team that are able to do this type of things. And given the time limitation I had, I think that's all I can give you today. So we started in the beginning with the story of Alice. In order to understand that the mathematical optimization problem revolves about naming your decisions, knowing what you can decide upon, Alice could not decide upon things like the existence of gravity. Well, she cannot deny gravity. She could not change the rose itself. I mean, she could have cut it, but I took that out of the problem. So she had a rose, she had a glass of water. The only decision she had that she could take by herself was the amount of water. So that's the first thing you need to be able to name are the decisions that you can take. Those are your decision variables. Then you need your objective function, which is the thing that you want to improve, either by maximizing or minimizing. Then you have your constraints, and then you are done. And once you have expressed that in a proper mathematical way, and you can translate it into code, for instance, using Pyomo as a package to do the modeling of your decision problem, then you can use a solver to find the optimal solution. And then you are one step further. In this case, you know which hospitals to open to serve the highest possible part of the population for that budget. Was my story clear to you? Did you get an idea of what mathematical optimization is all about? I'm inviting any of you to unmute and answer this question from your own perspective. Did you get an idea of what is mathematical optimization? If you hear the term later on, somebody talks about, let's use mathematical optimization. Some people call it mathematical programming. That was a name used years back, but now the community is more or less reserving the term programming for the actual coding and replacing mathematical programming by mathematical optimization. So if somebody mentions, let's use mathematical optimization, that you know now that it entails the translation of the reality to a mathematical model and the usage of a solver to find a solution. Did that land on you? Heva is raising a thumb. Okay. Oh, Esme also. Thank you, ladies. Thank you, Vladimir. Okay, that landed on you. So now you know if somebody talks about mathematical optimization, you know more or less what it is all about. Did this add value to the stories of Brit and Parvati about pizza? Ayman says that it's going to need a lot of time to digest this. I understand, Ayman, I understand. Did you enjoy these 2 hours and a half? Did you like this training somehow? Of course, that you are all very polite. You are all going to say yes because you don't want to hurt me. Honey is giving me a heart. Oh, lovely, lovely, lovely. Oh, I get another one from Kevin. Well, you are very, very kind, and it's not even Christmas time, so I'm probably going to believe you. Did you feel like I want to play with those notebooks? I want to try to do a little bit by myself. Is there anybody that, oh, Zoe is looking forward to play with my notebooks? And let's see. I hope I'm saying your name correctly also. Okay.
Yes, thank you so much. My name is Silitsazi from Lesotho, the southern parts of Africa.
Yes.
And thank you for the presentation. And you just put mathematics in a simpler way and make it so simple that and find a way, open my mind that mathematics can be used in any sector. And coding is one of the optimizer. Thank you.
Oh, you are so welcome. Yes, that's the impression I wanted to pass to you. Don't be afraid of mathematics. You don't have to learn everything by yourself. You just need to team up with people that know these things and to have the feeling, okay, I can use this knowledge if I want to bring my project further. And
I think we lost him for a sec.
It's part of the storyline.
Oh my God. Okay.
No, we
Maybe
really
he's gonna join. Okay. Let's see. Well, maybe you can put all your nice comments in the evaluation form and I will send it to him. Let's see if he joins back. Mm. Mm. Okay, maybe he actually has some connection problems. So I would say that if you have any questions, you can send them to me on Slack, and I will ask the professor to answer them for you. And I will also let him know that everybody says thank you and that you guys like the session. This is also the last session. So in the past few, in the next few days, we will let you know about your mentors, so that you can start scheduling sessions with them and start working on your project. So I'm really looking forward for that. yeah, we read all your projects and they're all very interesting. We're now going through the matching with the right mentors. So we will let you know as soon as we have that. But in the meantime, thank you very much for participating in the classes. I really hope that they were helpful coming from all the team. And as always, if you have any questions, you can reach out to us on Slack or on email or whatever you prefer. Thank you very much. Bye-bye.
Thank you.
Thank you. Bye-bye.
Thank you. Bye-bye.
Okay, thank you.
Thank you. Bye-bye.
Bye-bye.